we want to do on these next few problems is refresh our memories on the basic rules for derivatives and notation. We'll start here with the derivative with respect to x of x cubed over e to the x. So since this is set up as a quotient, we'll jump into applying the quotient rule. So here what we'll do is start with the bottom function e to the x times the derivative of the top. So we'll have e to the x times the derivative of x cubed is 3x squared minus the top function x cubed times the derivative of the bottom function. Well, the derivative of e to the x is just e to the x. And then all over the bottom function squared. So that's e to the x squared. Now let's practice our simplifying. In the numerator here, we want to factor out what's in common between these two terms. So both terms have an e to the x in common, and we can factor out an x squared. So we're going to factor out an e to the x and an x squared. And what would have left from the first term is a 3. So just this 3, and then we'll have minus from the second term. If we take out e to the x and x squared, we'll have one copy of x left, so just x to the first. And then all over, well, e to the x squared is 2 copies of e to the x, so I'm going to write that as e to the x times e to the x, just so that I could clearly see right now that in the numerator and denominator, I have an e to the x that is a factor in both, which is why I'm allowed to cancel, because this e to the x over e to the x is just a 1. So what I have left is x squared times the quantity 3 minus x all over e to the x. A couple things I want to point out and remind us about. Again, the notation. So this is saying to take the derivative with respect to x of this function. And so we can just jump straight into the derivative. This is the answer in the next line, which is why we removed the operator here. And so this is the answer, and then we just simplified it. Another quick thing to point out is that we did not have to use the quotient rule here. What we could have done is rewritten the problem as x cubed times e to the negative x. And this would have been a product rule with the chain rule involved. And we'll practice the product rule in the next problem. In this example, we're told to find f prime of x, or find the derivative of f, given f of x is equal to x over 4 minus x times natural log x. So here we have two terms. Terms are separated by addition or subtraction, and we would find the derivative of each term separately. Now, this first term here, x over 4, while it is written as a quotient, I don't need to apply the quotient rule in order to find the derivative. What I can do instead is think about how x over 4 is the same as 1/4 times x. So I'm going to rewrite the function for a second, because now the derivative of 1/4 times x is just 1/4. So I can start by saying that the derivative f prime of x is equal to 1/4. But now the second term is a product of two functions of x. So I have x times natural log x. So that's going to require the product rule here. So we're going to have 1/4 minus, and the product rule, as a reminder, is going to end up becoming two terms itself. So since this is subtraction here, I do want to make sure and open parentheses, since the product rule is going to yield two terms. So the product rule here is going to say take the one function, I'm going to start with the first function, x, and then times the derivative of this second function here, natural log x. The derivative of natural log x is 1 over x, plus, then we're going to leave natural log x alone this time, so plus natural log x times the derivative of that first function, x, which is just 1. So the product rule, we leave one function alone, take the derivative of the other function, plus, and then we switch. So whichever one we took the derivative of, we leave that alone, times the derivative of the other function. And so now it's just a matter of simplifying here. So I have 1/4 minus, now x times 1 over x, that's just 1. I'm going to leave that in parentheses, plus natural log x. And this negative would then distribute to both terms. So I have 1/4 minus 1 minus natural log x. And 1/4 minus 1, that's -3/4 minus the natural log of x. Before moving on, just a quick note about notation. This function was called f of x, and between the first line and the second line, we just rewrote the original function. So notice that this is just equals the previous line. But from the second line to the third line, we began the derivative, so we need to change the function to f prime of x at that point. In this example, I'm given y equals natural log of the quantity 3t squared plus 1, and we want to find dy dt. So find the derivative of the function y with respect to the variable t. My function is a composition, natural log of the quantity 3t squared plus 1. This is not multiplication, so this would not be the product rule. So we need to use the chain rule when I have a composition. And so the chain rule, how that's going to work here is to find dy dt. So dy dt, the derivative of y with respect to t is going to be, well, the chain rule says we want the derivative of the outside function, so f prime, of the inside function. So we're going to leave that inside function while taking the derivative of the outside function. So the derivative of natural log of t is 1 over t. But our inside function is 3t squared plus 1. So we're going to start by saying 1 over 3t squared plus 1. So what we've done is f prime of g of t. So the derivative of the outside while leaving the inside the same. And then the rest of the chain rule says now times, we're going to multiply by the derivative of that inside function. So we're going to have times the derivative of the inside, just a power rule, is 6t. And so really what happens is that inside derivative can be multiplied to the numerator. So we end up with the final answer here of 6t over 3t squared plus 1. And now let's find the derivative with respect to x of e to the x squared minus 2 over x. So we have two terms. We would take the derivative of each term separately. The first term, e to the x squared, is a composition. So we have x squared inside of e to the x. So this is going to need the chain rule. And then 2 over x. So while it is a quotient, we wouldn't use the quotient rule. So what I'm going to do is start this problem by rewriting that second term. So e to the x squared, I'm going to leave alone. But instead of taking the derivative in the form 2 over x, I'm going to rewrite this as 2x to the -1. And then I can just use the power rule instead of thinking about this as a quotient and using the quotient rule. Notice that I kept the derivative operator here because I haven't taken a derivative yet. From this line to this line, I'm just rewriting the function. So now let's take the derivative, which means I'm going to lose the operator. The derivative of e to the x squared, well, again, that's a chain rule. So the outer function is e to the x. So the derivative of e to the x is e to the x, but we have an x squared in the place of x. So we're going to leave the inside function the same. So it's just e to the x squared. And the rest of the chain rule says times the derivative of that inside function. So times the derivative of x squared, which is times 2x. So now, moving on to the derivative of the second term here, we can just use that power rule. So -1 times that -2 in the front, that's going to be plus 2x to the -2. So I'll subtract 1 from the exponent here. So what I have is 2x e to the x squared plus, I can rewrite that second term as a quotient again. I have 2 over x squared. And now I'm actually going to combine these together into one quotient. So I would write these with common denominators. I'd multiply the top and bottom on the left side by x squared. So I'd have 2x cubed e to the x squared over x squared plus 2 over x squared. So this x to the first became x cubed because I multiplied by an x squared. So now that these have common denominators, we can write them as one fraction. So 2x cubed e to the x squared plus 2 all over x squared. And that's just for some more simplification practice. I can actually take the 2 out of the numerator here. So I'd have 2x cubed e to the x squared plus 1 all over x squared. Now, in general, is it necessary to simplify that much? No, not if we're just asked to find the derivative, but depending on the context of the problem where we might need to take a derivative and then use it for something else, we want to be able to simplify as much as possible depending on the problem.